is the first one in the fall. Today, we are honored to have Professor Wenzhen Li as our webinar speaker on green ammonia mediated CO2 capture and electron reduction to valuable chemicals. Before providing more information about Professor Wenzhen Li, so I just want to make sure that our GPS President GP has anything to say. I don't see GP. Okay, let's move forward to introduce Professor Wenzhen Li. Professor Wenzhen Li is a professor, the Stiles Herbert Faculty Fellows in the Department of Chemical and Biological Engineering at our state university. Dr. Li received his PhD with honors from the Dalian Institute of Chemical Physics at the Chinese Academy of Sciences in 2004. He worked as a postdoc researcher with Professor Masahiro Wananabe in University of Yamanashi, and also with Professor Yushan Yan in the University of California, Riverside. He also worked as a research scientist in SUNY and Alberni College of Nanoscale Science and Engineering before he moved to our state university in 2014. His research interests are in the areas of catalysis, electrochemical energy, biorenewables, and advanced materials. Dr. Li has published over 125 articles with over 18,000 citations, and he also holds 8 issued patents. His current H index is 70. Dr. Li's current research activities include advanced electrocatalysis, electrochemical conversion of biomass feedstock to chemicals and fuels, green fertilizers, carbon dioxide capture and conversion, selective electrocatalytic alcohol oxidation, and innovative pair electrolyzer design. Before we move on to the webinar, there are a few things we'd like to request from the audience. So please remain muted during the webinar. If you have questions, you are encouraged to submit a question to the question drop box and not wait till the end. Without further ado, the floor is yours, Professor Wenzhen Li.
Thank you so much for the kind invitation and the kind introduction. Now let me share my slides with you. My pointer. Okay,
Yep.
it's good. Okay, so
Yep.
is my voice heard well?
Yeah, this is good.
Okay, good.
Yep.
Yeah, okay. A little bit more. Okay, thank you so much, Long and Luke, for your kind invitation and hosting my seminar. I'm very happy to be here to give my presentation in green ammonia mediated CO2 capture and electron reduction to valuable chemicals. Okay, so let's move to introduce the big picture. As we all know, the increase in atmospheric carbon dioxide concentration from 280 to 420 ppm since the early 19th century has led to the average global temperature increase about 1.2 centigrade. This has led to some severe global warming and climate change issues. In order to keep within 2-degree goal set by the Paris Agreement, approximately 10 gigaton carbon dioxide per year must be captured. But in another aspect, carbon-based chemicals and polymers are the pillars to support our modern society. They have a huge global market value of over 300 billion and are still produced predominantly from non-renewable fossil sources through thermochemical process. There is an urgent need for sustainable manufacturing of carbon-based chemicals using waste or renewable carbon, like CO2. So among different approaches, electrochemical reduction of CO2 to valuable chemicals have attracted enormous attention, and it can be directly powered by renewable energy, such as wind and solar. So now I'm going to show you, this renewable energy at Iowa. But probably you know that with more and more electricity generated from renewable sources, such as solar and wind, we're moving towards a more electrified society. So we have seen more electric cars on streets, hopefully more chemicals produced from renewable process. And we also know wind is a strong renewable energy source. Onshore turbine can generate electricity about 3 megawatts, which can power more than 1,500 households. The state of Iowa actually generated 59% renewable, it's electricity from wind. It is ranks #1 in the United States. It has the lower industry electricity rate by 19% than the national average. But more importantly, there is about 2.5 curtailment rate. So that means 2.5 times was cut even in a very strong windy day. So with the renewable electricity can be accumulated up to 7.7 billion kilowatt hour annually. So this can provide a huge amount of energy for distributed chemical manufacturing. So as I show you here, see here is the video on the surface. You can see there are some turbines here, wind turbines. But even in quite strong wind, a strong wind, it doesn't. Well, you can see faster. There is the need. We can use this renewable energy to power future chemical manufacturing. So most carbon dioxide electrolyzers must be fed with pressurized and high purity CO2 gas. But unfortunately, capturing with the CO2 from this dilute source usually requires energy and capital-intensive recovery and pressurization process. For example, the release of CO2 is accomplished by heating the capture media at up to 150 centigrade. So therefore, coupling CO2 capture and electrochemical CO2 reduction is critical to decrease energy cost and make the overall process more economically feasible. So in our lab, we are studying synergizing green ammonia production and CO2 capture and utilization. Here is our overall proposed process. We can concentrate dilute waste liquid nitrogen from, for example, agriculture wastewater using electrodialysis. And then we feed the concentrated nitrogen stream into our self-developed alkaline electrolyzer to produce single ammonia product. And the produced ammonia can be captured by acid to make fertilizer, or just with water to make ammonia a solution to power fuel cell, direct ammonia fuel cell. Or more importantly, we can capture CO2 to form ammonia bicarbonate. Then feed ammonia bicarbonate in an electrolyzer so it can produce formate of CO, hydrogen, and synthetic gas. So without nitrates, so this electrolyzer can serve as a hydrogen producer, or it may be combined with this reactive nitrogen source directly with CO2 to produce urea or other carbon nitrogen containing chemicals. So my talk will be focused on 3 parts. First is green ammonia synthesis from waste reactive nitrogen. Second is electrochemical reduction of ammonium bicarbonate solution to valuable chemicals, CO and formate. And finally, I will briefly introduce our research on CO2 absorption by ammonia solution. So let me first start from the general nitrogen cycle. The nitrogen cycle is a biogeochemical cycle through which nitrogen is converted into multiple chemical forms as it circulates among atmospheric, terrestrial, and marine ecosystems. The conversion of nitrogen can be carried out through both biological or physical process. But this reactive nitrogen, for short name NR, includes all nitrogen-containing species except for molecular nitrogen, N2, in the air. Reactive nitrogen is an essential nutrient that builds proteins on which our human health relies. So in industry, ammonia is actually produced through a Haber-Bosch process established over 100 years. So every year, over 175 million tons of ammonia be produced through the Haber-Bosch process. But it requires harsh conditions, like high temperature, actually temperature not that high, but the pressure is quite high, can go up to 250 bar, as well as centralized facilities for large amount of ammonia production. It also repairs molecular hydrogen. That is problem come from because we use methane reforming to get hydrogen, so it stoichiometrically dump CO2 to the environment. So it is about 1.44% of total CO2 emission just for ammonia synthesis. So therefore, it is urgent need to explore sustainable and scale flexible routes for ammonia production. So to replace the steam methane reforming here and the Haber-Bosch process for ammonia synthesis with huge amount of CO2 emission, the researchers can use green hydrogen for Haber-Bosch process reaction. So basically, we can get hydrogen from water electrolyzer and use this hydrogen to for Haber-Bosch process to get ammonia. So, if a more advanced route is to explore photoelectrochemical approach to synthesis ammonia. Directly use water as the proton source. So if the electric grid is supplied by renewable energy, it has less CO2 emission. It can operate under mild conditions and can reduce transportation and storage cost. But unfortunately, current electrochemical synthesis of ammonia at ambient conditions are very, very inefficient. The nitrogen-nitrogen triple bond has a very high bond energy, up to 941 kilojoule per mole, so making very sluggish kinetics and electrochemical reactor design literally impractical currently. But in another aspect, human activities have contributed to half of the total reactive nitrogen generation. So here is a number. The total fixed nitrogen is 413 petagram nitrogen per year, in which the fixed nitrogen by Haber-Bosch process is around 150 petagram nitrogen per year, while only about 290 petagram nitrogen is returned back to molecular nitrogen. So this means denitrification of these reactive nitrogens have a lower rate than the nitrogen fixation rate, so causing the accumulation of reactive nitrogen in the ecosystem, such as eutrophication in agricultural water bodies. Importantly, denitrification process sometimes can release nitrous oxide, N2O. Okay, that is more severe GHG gas than CO2, more than 300 times severe than CO2. In fact, restoring balance to the nitrogen cycle has been identified as one of the grand engineering challenge by US National Academy of Engineering. So actually, if we look at the freely accessible nitrogen sources, we have abundant source of reactive nitrogen, but of course, molecular nitrogen is much more abundant than the waste reactive nitrogen. But still, you can find that it's about 3 orders of magnitude organic nitrogen as compared to ammonia needed. So simple math shown here. So if we can use all these denitrified, we use this denitrified rate and to feed the ammonia production through Haber-Bosch process, so it can achieve about 82% of the global ammonia demand. So the advantage for converting reactive nitrogen to ammonia includes, it can mitigate their environmental impacts. It can avoid generation of N2O through quick formation of nitrogen hydrogen bond with ammonia, and it reduces ammonia demand and the environmental impact from nitrogen fixing Haber-Bosch process. So in our lab, we developed an integrated sustainable process for upcycling reactive nitrogen, first both on nitrate, but then expanded to diverse waste nitrogen source. So basically, we used the electrodialyzer to concentrate the dilute nitrate to high concentration nitrate. Then we developed alkaline electrolyzer to convert nitrate to ammonia. Then that can be captured to make a nitrogen fertilizer or capture CO2 for its further upgrading. So we thank Dr. Gu and his group at Wichita State University in Kansas on electrodialysis study. So basically, they develop a effective electrodialyzer to convert to concentrate dilute nitrate streams, usually from tens of hundreds of ppm nitrogen to 1 to 2 more. That's workable for electrolyzer. So this is the first step of our electrodialyzer and the electrolyzer integrated process. So here is a three-membrane ion exchange membrane-based electrodialyzer, through which high concentration nitrate of up to 2 more can be obtained. And the electrolyzer operated at 1 milliampere per centimeter square, but quite low, cell voltage is as low as 0.4 to 0.8 volt. We have experimentally demonstrated that the low pair voltage for concentrating nitrate by electrodialysis is achievable and predictable. Very interestingly, we found that the coulombic efficiency for nitrate concentration can go up to 96%. Then we use this concentrated nitrate as a feedstock to our self-developed membrane-free alkaline electrolyzer, what we call MFAEL, for ammonia electrosynthesis. So MFAEL is inexpensive and robust. We use commercial available nickel mesh or foam as both cathode and anode electrode. The electrolyte is concentrated NaOH, KOH with 40 weight percent. That's about 15 more OH concentration. On the cathode, nitrate can be reduced to ammonia under nitrogen. More interestingly, can under air flowing. So it leaves out of the reactor and can be absorbed by water, acid, or CO2. And the reactor can operate it at relatively low temperature, for example, 80 centigrade. So we first studied a small-sized alkaline electrolyzer of 150 milliliter, and we optimized some operation conditions. You can find that both nickel electrodes in mesh and foam, they showed higher nitrate reduction performance to ammonia in wide range of current density and in wide range of the temperature. So usually, when you increase the temperature, the reaction kinetics improve. To also confirm that nitrate to ammonia transformation is through electrochemical reduction process. As you can see that without applying potential or feeding of nitrate or just feeding hydrogen without potential, we cannot reduce nitrate to get ammonia. So first, this is the electrochemical reduction process. So with the concentrated NaOH, KOH electrolyte, we achieved a record high performance of ammonia electrosynthesis from nitrate reduction. So basically, we obtained 4.22 ampere per centimeter square partial current density for ammonia production with up to 85% of Faraday efficiency at 4.5 volt cell voltage operation. So we used the online GC to quantify the products, and we found that the side reactions HER can be effectively suppressed. Only about 5.4 Faraday efficiency towards hydrogen. And also, no nitrogen was detected. So this means nitrate is predominantly reduced to ammonia, no nitrogen or other nitrogen gas products. So our work is better to most than most of previously published work using advanced catalyst listed here for nitrate reduction to ammonia, as shown in this figure. We further studied the water content and the alkaline concentration effects. We can find that at a higher alkaline factor, higher conversion can be achieved with a higher Faraday efficiency to ammonia. We also found that ammonia lacks escape evolved from the reactor at higher base concentration conditions. So there is no obvious difference in nitrate conversion and Faraday efficiency to ammonia when AOH, KOH, or their mixture, one-to-one mixture electrolytes used. So this suggests that the effect of a cation is not apparent at high alkalinity. Next, we studied the effect of carrier gas and metal catalyst on the nitrate reduction performance. So as you can see that the nitrate conversion and the Faraday efficiency to ammonia do not change when the carrier gas was changed from inert nitrogen to air containing 21% of oxygen or pure oxygen. So this is good because it means that the produced ammonia is not further oxidized as anode under oxygen-containing environment. Think about that. So we use membrane-free electrolyzer. The anode oxygen evolution reaction is a counter reaction. So this also means that we can just use cheap air as a carrier gas to produce ammonia out of the reactor. We also tested other metals, including ruthenium, copper, cobalt, and nickel for nitrate reduction in the high pH electrolyzer. We found that the ammonia Faraday efficiency kind of varies from 32 to 39. It's average like 30, 35. And cell voltage about 3.5 volt for very high current density operation, 1 ampere per centimeter square. Is higher than the usually used industrial relevant current density. So this indicates that no apparent difference among the tested metals for nitrate reduction in such high alkaline electrolyte. Also, our alkaline electrolyzer is easy to be scaled up. So we have successfully scaled it from 150 milliliter to about 2.5 liter. So we use a larger nickel mesh of 100 centimeters square as the for both cathode and anode. And the scaled alkaline electrolyzer can deliver 25 ampere current, equivalent to 250 milliampere per centimeter square current density. And we obtained a reasonable Faraday efficiency of 70%, and it can run over 24 hours as we tested. It is interesting to find that the cell voltage actually decreased from 3.5 to 2.8 volts due to the regular temperature increase at such high current density operation. And the produced ammonia can be captured by acid, CO2, and water with nearly 100% collection efficiency. I know that by using CO2 as capturing agent, ammonium bicarbonate, high purity, can be filtered out and white powder can be collected. So finally, we demonstrate that the direct ammonium fuel cell can deliver a peak power density of 35 milliwatt per centimeter square, quite elegant without modification on catalyst, electrode structure, and operation conditions. So we further studied electrochemical conversion of waste nitrogen feedstock containing nitrogen-oxygen bonds and carbon-nitrogen bonds from organic waste to single product ammonia in our alkaline electrolyzer. So our screening test results from different form of reactive nitrogen is shown here. The electrolysis was carried out at 25 milliampere per centimeter square with 0.2 millimole of added reactive nitrogen for each chemical. And ammonia was collected every half hours. We use different color bar to show each half hour. And the y-axis shows ammonia nitrogen recovery efficiency. So that corresponds to the ratio of produced ammonia to the initial added reactive nitrogen this nitrogen, okay? And each color block represents half-hour period amount. We can find that our alkaline electrolyzer can convert various forms of reactive nitrogen chemicals into only product ammonia with high recovery efficiency. Although the reaction kinetics can be quite different and depend on the structure of your feedstock. But more colorful bars means a slow reaction kinetics because it needs a longer time. But this also indicates that our alkaline electrolyzer is a convergent reactor. It can produce ammonia from both inorganic waste, nitrogen-containing nitrogen-oxygen bond as a cathode, and carbon-nitrogen bond as anode in this membrane-free electrochemical reactor. So next, we focused on revealing the carbon-nitrogen breaking mechanism for electrochemical oxidation of organic nitrogen-containing compound. So we used isotopic 13 carbon labeled glycine and alanine as feedstock, and quantitative produced products using NMR. Based on the product analysis, we can deduce which carbon-nitrogen bond is cleaved and even the overall reaction mechanism. So for example, if we use the glycine with 13 carbon labeled on the second carbon as the reactant, so 13 carbon labeled oxalate was observed. So that indicates this carbon-nitrogen bond cleaved, okay? Because ammonia is observed as another product. So this also shows that carbon-nitrogen bond cleavage is more favorable than carbon-carbon bond breaking. So this is further confirmed by the 13 carbon labeled analysis. So ammonia was observed as a product suggesting carbon-nitrogen bond cleavage is relatively easy. But after carbon-nitrogen bond cleavage, so the carbon-3 carboxylic intermediate is further converted to acetate and carbonate, so indicating this carbon-carbon bond, the carboxylic acid contained carbon bond cleaved instead of this methyl group contained carbon-carbon bond cleaved. So we labeled another carbon, get the same result. So that's the beauty of using isotopic labeling, right? So basically we can, find the reaction pathway. So the conclusion is carbon-nitrogen bond is favorable more than carbon-carbon bond, but if your carbon-carbon bond linked with a saturated functional group like carboxylic acid, that carbon-carbon bond preferably break, right? So if this carbon-carbon bond break, you will get the same oxalate instead of acetate. Hopefully, I showed this mechanism we currently and our current understanding of the carbon-nitrogen bond cleavage. Then we compare nitrate reduction with amino acid oxidation. So here we use aniline oxidation in our alkaline electrolyzer. Again, we use the 15 nitrogen to label nitrate. Okay, and then so we can separately quantify 14 ammonia and 15 ammonia because 15 ammonia is produced from nitrate. It's from nitrate reduction. 14 ammonia produced from oxidation of alanine. Okay, therefore we can find the cathode and anode Faraday efficiency to ammonia separately. Okay, here is the conclusion. We found that about 27% Faraday efficiency, cathodic Faraday efficiency to ammonia, while only 52% of anodic Faraday efficiency to ammonia production. So they come from nitrate reduction and aniline oxidation. So this suggests that our alkaline electrolyzer is a convergent reactor to produce single product ammonia from both sides, both electrodes. So finally, we did some primary techno-economic analysis on this integrated system. We found that the levelized total cost, LTC, for the concentrating of nitrate from dilute to 2 mole with 80% of recovery only costs about $5.75 per kilo more nitrate. However, the LTC for ammonia synthesis is through nitrate reduction at this current density, industry relevant current density, the cost can go up to 44.8 per kilo more ammonia. To know that the market price for ammonia current for the 5 years is about 1,500 per ton of ammonia. So that means our integrated process and the current utility bill, and by combining electrodialyzer and electrolyzer, is about $50.5 per kilo more ammonia. That's about $3,000 per ton. It's almost double the current price. But we don't consider with the feedstocks credit. So the cost of concentrations through electrolyzer, electrodialyzer is lower than the cost of electrolysis. As a key to make the overall process more economically attractive is surely to lower the electricity cost. Know that here we use 7 cents per kilowatt hour. So think about if renewable electricity bill can drop down like 1 cent, overall process will make more sense. So now I'm going to move to the second topic, integration of green ammonia production and CO2 capture and reduction. So DOE Office of Fossil Energy and Carbon Management is seeking for innovative system that can integrate CO2 capture from a dilute gas stream and CO2 conversion into value-added products without requiring extra purified CO2 intermediate stream. Okay, so we actually can integrate green ammonia production from waste reactive nitrogen and reactive CO2 capture and reduction together. And I have shown you the green ammonia can be produced from waste nitrogen feedstocks, and it can be used as reactive carbon capture agent for the next CO2 conversion. I'd thank my former PhD students, Heng Zhou, Yifu, and Dr. Li Junko. As you know, ammonia is one of the largest commodity chemical. Its cost is relatively cheap, like $1,500 per ton. It can be converted to about 25.5 kilo more ammonia versus 183 equivalent to kilo more MEA to capture 1 kilo more of 1 kilo more CO2. So the capture reaction equation is here. The tricky thing is, you just need one more of ammonia to capture CO2. Well, you need 2 more of organic amine to capture CO2. Okay. Another big advantage is ammonium bicarbonate has very low decomposition temperature. It's only like 36 centigrade. So it can serve as the reactive capture agent for in situ CO2 generation and reduction to valuable chemicals. I'm going to show you two examples. First is to formate production. Second is for CO production. So next, I'm going to show you this captured CO2 reduction to formate on electrodeposited bismuth catalyst. So basically, we use the regular electrodeposition method to prepare bismuth catalyst deposit on carbon paper. So SEM image and XRD patterns show, the relative uniform deposition of metallic bismuth particle on carbon paper substitute. So we first test the electrolysis of 2.5 more potassium bicarbonate, ammonium bicarbonate, and MEA captured CO2 at 40 centigrade. We found that ammonium bicarbonate shows the highest Faraday efficiency to formate, about 80%. That is higher than KOH and MEA as the capture agent. The Faraday efficiency to formate dropped when the operation current density increased from 100 to 300 milliampere per centimeter square. Okay, hydrogen gradually becomes to the dominant product. We also found that with temperature increasing, the Faraday efficiency to formate increases for both potassium bicarbonate, ammonium bicarbonate, as shown in this figure. So we compared the different membrane-based electrolyzer, namely bipolar membrane-based, cation exchange membrane-based, and anion exchange membrane-based electrolyzer. So we found that the AEM-based electrolyzer for ammonia bicarbonate electrolysis can reduce cell voltage significantly by 1.3 volts, equal to about 35% as compared to a BPM-based one. And the in situ generated CO2 is in the south is quite complicated because not only temperature effect leading to thermal decomposition of ammonium to get CO2, the local pH shift also produce CO2 from bicarbonate. If you lower down the pH, right, shift to the acid side, and CO2 can be generated. So by using AEM, the Faraday efficiency to formate can reach nearly 90% at 100 milliampere per centimeter square at 40 centidegree operation. So this result is higher than lots of previous reported work. So we are now currently working on a large surface area bismuth catalyst. That one is derived from moss. So we can reach even higher current density and maintain the Faraday efficiency. So we also test the durability of electrolysis of ammonium bicarbonate, and shown here. So we found stable operation for about 5 hours, and the cell voltage maintained at 2.1 volts, at Faraday efficiency to formate around 75 to 80%, and the minimum amount of formate crossed from cathode to the anode. So we designed a second ammonia absorbing vessel containing sulfuric acid to collect escaped ammonia. We quantified both ammonium in the cathode and in the sulfuric acid trapping solution by using NMR. So basically, we found that the ammonium concentration in the cathode doesn't change, while the absolute amount of ammonium captured by the acid is also negligible. It's about 0.07% of ammonia escaped from the system. So we calculate the efficiency of ammonia-mediated CO2 capture and reduction, including nitrate reduction to ammonia utilization for CO2 capture, and Faraday efficiency to ammonium bicarbonate reduction to formate. And the first and the second steps reach all around 100% efficiency, while the last step is about 70%, suggesting a better catalyst could be further installed to further improve Faraday efficiency to formate, especially at higher current density operation. Its higher current density means higher production rate. But it's worth to mention that the XRD patterns shows that our CO2 captured ammonia produced ammonium bicarbonate has very similar XRD patterns as high purity commercial ammonium bicarbonate. So indicate that this process can produce high purity chemical ammonium bicarbonate at significant amount. So we can get like 74.2 grams from this process. So next, I'm going to present our very recent work in exploring single atom nickel catalyst for CO2 reduction to CO from ammonium solution. So we are collaborating with Dr. Qi from Ames Lab and Dr. Huang from our chemistry department on this project. So first, they synthesized single atom catalyst, nickel-based single atom catalyst through a template calcination process. From XRD patterns, we can find that no detectable nickel diffraction peak from this nickel single atom catalyst, indicating that no nickel nanoparticles are formed, and carbon is the most abundant element. Nitrogen ligand connecting nickel and carbon planes can be confirmed. So SEM EDEX show that single metallic atoms are directly revealed as the bright dots dispersed on carbon support without any notable presence of nanoparticles. So indicating successful synthesis of this single atom catalyst. Then my student Su Jin Kang designed a bipolar membrane-based electrolyzer for ammonium bicarbonate reduction to CO. Okay, so the proposed steps are shown here. So we can get in situ generated CO2, for short ICO2, from two sources. One is from thermal decomposition, the red highlighted reaction, and the blue highlighted reaction. So that is pH shift, right? When you reduce the pH, you get more proton, you reduce bicarbonate to get ICO2. And then this ICO2 can be fed to in situ generated CO2 can be reduced to get CO with high performance. So we found that superior RD efficiency to CO at about 56% on this nickel single atom catalyst than commercial silver nanoparticle catalyst. For the efficiency to CO only 28% with potassium bicarbonate feeding. But in the sharp contrary, silver nanoparticle catalyst showed very low performance to CO, lower than 1% when the solution is switched to ammonium bicarbonate. While the nickel-based single atom catalyst electrode still maintains 45% Faraday efficiency to CO. We also use nickel nanoparticle as comparison. You can see that nickel basically is a good HER catalyst, but not a CO2 reduction catalyst. So this means that using single atom catalyst can effectively avoid poisoning of ammonium on silver electrode. We also found that CO2 performance is less dependent on the metal cation type, as I shown here, as compared to silver nanoparticle. The weak cation sensitivity allows selective CO2 reduction in a relatively universal absorbent media. So we are working on Dr. Bing Wang group on theoretical study to explain why single atom nickel catalyst can tolerate ammonium poisoning during ammonium bicarbonate electrolysis. So we found that the CO2 reduction to CO performance follows this trend. So bicarbonate is higher than carbonate and higher than carbamate. I'm going to show you some slides on what are the nitrogen carbon species when CO2 absorbed by ammonia. But finally, we conducted a durability test of nickel single atom catalyst at 50 milliampere per centimeter square in the flow cell system. That shows a Faraday efficiency per CO at about 60-70% and stable cell voltage about 2.7 volts throughout a 10 hours durability test. This suggests that ammonium bicarbonate can serve for CO2 reduction to CO. So finally, I'd like to briefly introduce our preliminary results on CO2 absorption experimental results. So we simulated flue gas using 10% of CO2 in a inert gas. So which controls the gas flow rate as constant. We use a gas dispenser to make the simulated gas distribute more uniformly. Then we measure the escaped ammonia by 0.5 more sulfuric acid. So we try to get ammonia loss amount. So there are three main reactions that occurred during the neutralization reaction of CO2 and ammonia. First step is bicarbonate formation, and then carbamate formation. This carbamate, and then carbonate formation. Okay, so we use 13 carbon NMR, so we can quantify carbonate, and bicarbonate. So we found they all coexist during the absorption process. Carbonate and bicarbonate corresponding to one peak, but it shifts depending on its ratio between carbonate and bicarbonate. Then we can calculate the total absorbed carbon, so that is equal to the sum of carbonate, carbonate and bicarbonate. Then we can calculate CO2 absorption efficiency, that is total absorbed carbon divided by total CO2 supply. Okay, so we found that the CO2 absorption efficiency is close to 100% in the first 3 hours and then decrease. As more ammonia is consumed, carbamate and carbonate are converted to bicarbonate, and the absorption efficiency actually decrease. We also studied the concentration of nitrogen and carbon species versus time within the 6 hours experiment, as shown in this figure. And you can see that the total captured carbon species increased with time, and some ammonia actually evolved from the system. At the end of 6 hours, the ratio of carbon to nitrogen is about 0.6. That means you need nearly double ammonia to capture CO2 with a reasonable rate. And the detailed kinetic study is currently underway in our lab. So our experiment also suggests that the total escaped ammonia from CO2 absorption system, this absorption is conducted at room temperature. Within the 6 hours measurement is around 7, but it finally reached a plateau. The rate of ammonia evolution decrease as more of ammonia is converted to ammonium. Ammonia is stable in the solution during the absorption process. So it means with decreasing of pH, your ammonia is safe. So that's why our highly alkaline membraneless electrolyzer, ammonia doesn't like high pH, it's just evolved. So we can get like 100% recovery efficiency. But I should mention that managing ammonia in industry has been practiced for over a century. It's not that a big issue, but of course, if you lower down capturing absorption temperature, it can help prevent ammonia escaping. So more experiments are underway with CO2 capturing from other simulated flue gas. Finally, let me conclude my work. Hopefully through my presentation, I convinced you something. So the lower energy consumption was demonstrated to recover nitrate from low concentration, like 100 ppm nitrate nitrogen by efficient electrodialysis, step 1. And we demonstrate high performance nitrate to ammonia conversion in a scalable, versatile, and cost-effective alkaline reactor with NaOH, KOH mixed electrode. That's step 2. And the unique configuration of the alkaline electrolyzer allows for continued production of pure ammonia-based chemical without the need of additional separation process. Step 3. We also did some techno-economic analysis that show that economic competitive of upcycling with the nitrogen dilute source by this integrated sustainable process. Now we can pair nitrate reduction with oxidation of organic reactive nitrogen compounds. Okay, like amino acid. We actually also demonstrate some quite complicated waste, like algae in our alkaline electrolyzer that can transform nitrogen oxygen bond as carbon nitrogen bond into ammonia as a sole nitrogen containing final product. So we also demonstrate that ammonium bicarbonate fed electrolyzer with AEM outperforms state-of-art potassium bicarbonate electrolyzer with a BPM bipolar membrane that shows about 3 times increase in the in situ CO2 concentration, 23% decrease in formate Faraday efficiency, an increase in formate Faraday efficiency, and 35% reduction in the cell voltage. So our integrated process by combining ammonium bicarbonate electrolysis with CO2 capturing by on-site generated green ammonia from electro reduction of nitrate in the alkaline electrolyzer shows remarkable close to 100% utilization of CO2 capturing agent. Finally, the nickel-based single atom catalyst showed remarkable CO2 R to CO performance from ammonia captured solution, ammonium bicarbonate, and its unique capability to tolerate ammonium poisoning. So finally, ammonia can serve as a reactive agent to capture CO2 from simulated flue gas with high absorption carbon to nitrogen ratio. It reaches the theoretical limit of MEA, and we believe ammonia loss can be well managed. So finally, I'd like to thank all my previous and current students and postdocs, Ames list here, who did wonderful, excellent research related to this project. I also like to acknowledge the funding source from NSF, USDA, recently DOE, and some seeding funds from. So I'm grateful to all my collaborators listed here from our university, Ames Lab, Wichita State, and University of Oklahoma. We're all from our Great Plains states. Thank you so much for your time to listen to my seminar. I'll be very happy to take questions if you may have.
Well, thank you, Professor Li, for that nice talk today. If anybody's got some questions, please submit them to the Dropbox, or just say that you have a question and we can unmute you and let you ask your question. Maybe I'll start off, and I apologize if I missed this, but in the first part of your talk, talking about the electrodialysis
yes.
machine, what are the practical feedstocks that you're looking at for that, and how much do they have to be pre-treated? And I guess I'm just curious about where the source of that dilute nitrate comes from, and what has to be done to it to put that into that instrument.
Right. That's an excellent question. So I had this question a lot of times before. First, that's my collaborator at Wichita State in Kansas, Dr. Goose group did all the experiments. As far as I know, they use high purity nitrate, made the solution to simulate that. They didn't consider other, other ions. As far as concentration, yes, you are right. They demonstrate tens or hundreds of ppm and nitrogen, but in the agriculture wastewater, it can be as low as like 10 ppm, even in the agriculture active season. But some unique source like slaughterhouse, that downstream nitrate can go up to like 200 ppm. So that's why they use high purity nitrate. They make tens to 100 ppm nitrate solution. They did their electrodialysis work. But the beauty of the electrodialysis is you don't need much of energy input. I mean, in terms of cell voltage, you can reach quite high Coulombic efficiency. As I show you that based on the TA analysis, electrochemical reaction is electrochemical reduction of nitrate to ammonia is about order of magnitude higher than this electrodialysis. Honestly, I don't know what's going on if some other alien ions in the realistic wastewater, what's gonna happen.
Okay, thank you. Is there any other questions from our audience? If not, I think I'll hand it back to Long. I want to thank you again, Professor Li, for your presentation today, and I'll hand it over to Long to introduce next month's speaker.
Thank you, Graham. Thank you also, Professor Li, for the great talk. So our next presentation is from Dr. Basim Halak from Chevron Phillips Chemical. The talk he will be giving is aromatic technology, premier on purpose benzene production technology. So the talk will be October 18th. Thank you very much for your attention, and see you in October. Bye.